lecture. The end is in sight.
For the survivors.
Even for an infinitely repeated game, there must be an end. So what I'm going to talk about here comes back to the distinction I think Sergio was making about the different ways that we might think an equilibrium, a Nash equilibrium, could be reached. Roughly speaking, there are three such ways. One is players compute an equilibrium and play it, or alternatively, they work it out through Bayesian updating, rational learning. A somewhat less fully rational way of getting to equilibrium is through the sort of dynamics that Sergio and Drew were talking about, where players are trying to maximize their payoffs, but they may not have particularly rational learning rules. They're using some sort of heuristics, such as fictitious play or best response dynamics or whatever. And a third kind of dynamic, and that's what I'm going to be concentrating on here, is where there may be no rationality at all. The optimization, the as-if optimization comes through selective pressure. So think of biological evolution, where genes are not maximizing, but successful genes proliferate and unsuccessful ones die out. And I want to apply that kind of idea to the study of repeated games. Why repeated games? Well, that comes back to what I said in the very first lecture. Repeated games are important, in particular because they help resolve the conflict that we see in the prisoner's dilemma. In a one-shot prisoner's dilemma, there's a stark contrast between what is good for the players as a group, cooperating, and what is good for a player as an individual, defecting. And we know that if this game is repeated, that contrast is relaxed. That is, it may be possible to have cooperation align with self-interested behavior. And for that reason, the repeated games have been very widely used in applications in many fields. But as the Folk theorem for repeated games makes plain, there's a flaw in this theory, in that although cooperative behavior is a possible outcome, so is uncooperative behavior and a huge range of other behaviors. And when we talked about the Folk theorem, we said exactly what was possible and what was not possible. But what is possible is very large indeed. And that means that the theory doesn't make very sharp predictions, which is awkward when it comes to applications. Well, that's where evolution comes in. We sometimes think of evolutionary pressure as a force for greater efficiency. And when I use the term evolution, I'm not going to be specific about whether it's biological and evolution, where evolution takes place through biological reproduction, or cultural evolution, where reproduction takes place through imitation. But both kinds of evolution fall under the heading of the discussion. We might hope that evolutionary pressure will help eliminate or weed out uncooperative behavior, at least in the long run. And this is a view that was expressed quite forcefully in a book that came out about 30 years ago called The Evolution of Cooperation, a book by Robert Axelrod. And let me show you one of the central ideas in Axelrod. I'm going to put it a little bit differently from the way he did. He emphasized a particular cooperative strategy, tit for tat. I'm not going to emphasize tit for tat. But otherwise it's similar. Let's imagine that we have large population of players, and these players, for whatever reason, are identified with the strategies that they play. Perhaps they are genetically programmed to play these strategies, or perhaps they have hit upon these strategies through some kind of cultural evolutionary process, but they're identified with their strategies. And let's suppose that the strategies that initially everyone in the population is playing completely uncooperatively. So that's the strategy, always D. It's a repeated game strategy. Now let's imagine that there's a mutation, or put another way, there's a small group of players who are introduced into this population who don't play always D. They play a strategy which I'll call conditionally cooperates, which in the summer school has sometimes been called the Grimm trigger strategy, which is to play C as long as C has been played in the past, but otherwise play D. And now let's see what happens when this small proportion of conditionally cooperative players are introduced in the population. We can make a 2-by-2 table. So here's always D, and here's conditionally cooperate. Always D against itself is going to get a payoff of 0 every period. So its long-run average payoff is 0. Conditionally cooperative against always D is going to get hurt the first period. It's going to try to cooperate, and it's going to get a payoff of -1, but it's going to very quickly learn its lesson, and it's going to play D from that point on. And so if we're looking at a long-run average, it's going to be very close to 0, right? Similarly, always D against conditionally cooperate will do pretty well the first period. It'll get a payoff of 3, because conditionally cooperate is cooperating the first period. But after that, it'll be getting 0. So it's practically 0 in the long run. But conditionally cooperate against conditionally cooperate is going to do very well indeed. It's going to get 2. So if we think of how these two strategies do against the population, let's say there's a small fraction C who uses conditionally cooperate, a larger fraction 1 minus Q who play always D. Conditionally cooperate is going to do better on average against the population than always D. And in the language of evolutionary dynamics, conditionally cooperate will successfully invade this population of always D. Always D is not evolutionarily stable. It will not persist.
You need a group.
You need a group, yeah. One will not, that one mutant will not be enough. So the way this sometimes happens in biology is that there's an isolated group on some islands. Somehow the island gets connected to the mainlands. The mutants come in, and they.
But then your whole population is not always D. The population you start with, you have this island out there someplace, right? Who are playing CC, right?
Right.
And they can invade. But in a population that has always AD, yes, always
right.
D.
Yep.
One mutant.
One mutant is not enough.
One mutant won't work. Two mutants. Huh? Two mutants.
You need a small group, and the way this works in biology is that that you have two different groups who were previously isolated. One big, the always D. One small, connected up. The way that's actually the way it happens in cultural evolution too. You have a country which has a group of immigrants who come in, and the group of immigrants have a particular practice which the domestic population don't have, but the immigrants' practice works really well, and so eventually the people in the domestic population adopt it too. So this roughly speaking was Axelrod's idea, and it looks quite encouraging so far, but there's a problem with it. And that problem can be illustrated by a somewhat more complicated strategy called alt. So alt is a strategy which is not so cooperative. What it does is it goes back and forth between cooperating and deviating. So in the first period it cooperates, then it deviates, then it cooperates again. It goes back and forth until somehow the alternating pattern is broken. Perhaps the other player fails to go back and forth between C and D. And then after the alternating pattern is broken, alt plays D forever after.
They are all synchronized. They are synchronized?
Alt plays C in the first period, D in the second period, and continues to go back and forth until...
C in odd, D in even.
Right.
Okay.
That's it.
So they are synchronized.
Yeah. Now, can alt be invaded by another strategy? Alt's not very cooperative. It gets a long-run average payoff of 1 rather than 2, right? 0 half the time, 1 half the time, if it's playing another alt.
2 half the time. 0 and 2.
What did I say?
6, 0, and 1.
Oh, okay. 0, yes. 0 half the time, 2 half the time, averaging out to 1. Now notice, so suppose we made a table like this one. And we have some other strategy, SPrime, here. What would SPrime have to be in order to successfully invade a population of alts? Well, alt against itself gets 1. If SPrime did not go back and forth between C and D, it would get killed by alt. In the long run, it would get an average payoff of 0. So basically,
What's SPrime?
SPrime is some other strategy, some mutant that has been introduced into the population. A small group of mutants. SPrime against itself might do pretty well. So this could be 2. But if Q is small, then in order for SPrime to have any chance of doing well, it's going to have to alternate.
Alt is the best reply to itself.
That's right. So
first of all, against alt to do best reply.
That's right. So the only way that S' has a chance is if it actually alternates, in which case this is 1, in which case this actually has to be 1 too. So nothing that differs, nothing that is more cooperative than alts can possibly do well when the population consists of alts.
What about the strategy that says, I cooperate unless I've seen CD, CD by the other player, and then I do CD, CD?
It won't work because as soon as you fail to alternate, the other player plays D forever. You don't get a chance to adapt to alternation. It's already too late. It's already too late. So alternate, again, in the language of evolutionary dynamics, is evolutionarily stable, even though it is not cooperative. And the situation you can now see is even worse than that, because I talked about a strategy that went back and forth between C and D. Suppose instead we looked at a strategy which played C followed by 2 Ds. C followed by 2 Ds. And if there was a deviation from that pattern, play D forever. Well, that, for the same reason, is going to be uninvadable. We can go all the way to almost completely uncooperative behavior and still maintain evolutionary stability. Yeah.
Wouldn't every invade by anyone would just make the alt play always D from thereafter, and this makes the population very vulnerable to every invade?
I didn't quite catch your question.
The alt population is
Yeah.
strategy that you
Okay.
make it always be.
That's right. So you're saying that that the alt population is not going to do very well because every time there's a mutant that comes in and fails to alternate, that's going to cause the alt population to end up playing D every period.
A two-step invasion will work beautifully. First send somebody, force them to do D, or alt D, then they become alt D, and then comes the CC and takes over. So the CC has to be preceded by somebody that in fact is going to lose the battle, and then CC enters and takes it over.
I'm going to make a similar point, but in a slightly different way. One way of re-emphasizing the point you've just made is to point out that alt is a very inflexible strategy. That is, it relies on perfect synchronization, and if this perfect alternation does not occur, then it results in very bad payoff, a payoff of 0. So how would we expect it to perform if there's a small probability that strategies are not executed perfectly? So you may be programmed to play alt, but computers, machines sometimes fail to execute the programs that they are intended to follow. So what happens then? Well, let me look at this same kind of setup. Let's look at a mutant strategy SPrime, which does alternate. It starts out alternating, and like alt, it continues to alternate as long as the other player has followed the alternating pattern. But if the pattern is broken, as will eventually happen by mistake, if SPrime does not, at least immediately, play D, what it does is, in the period after the alternating pattern is broken, play C. You can think of playing C as extending an olive branch, or you can think of it as a way that SPrime is in effect signaling to the other player that it is willing, despite the breakdown in alternation, to cooperate. Let's suppose that the other player does the same thing and also cooperates in the period after the alternating pattern has broken. Well, then what SPrime will do, this is how SPrime is defined, is to play C forever after, except in periods where there are mistakes. If the other strategy...
Wait a minute. When does SPrime play... when does SPrime expect the other player to play C? Immediately in that
Yes.
period?
Yeah.
How does the other guy know whether it's a mistake or not?
Doesn't know. if there's a breakdown in the alternating pattern, S prime plays C the following period.
So that, the following period is going to be either CC, in which case S prime will play C forever, or CD, in which case S prime will play D forever. And that's it.
That's it.
It's all finished.
That's it. That's it. So does everyone understand how? Yes.
I understand the play C forever. So play C no matter what happens after that.
Yeah.
Okay.
Yeah. So now let's compare S prime with alt using one of these tables. Now we don't act. There's no difference between S prime and alt as long as there's never been a deviation from the alternating pattern. So we don't have to look at that case. We only have to look at the case starting from a point where the alternating pattern has broken down. That's the only time they're different. Well, in that case, alt against alt gets 0 because it plays D every period. S prime against alt does badly in the first period because it cooperates that first period, but after that it plays D, so it's going to get 0. Alt against S prime gets 0, but S prime against S prime gets a payoff of 2. And so again, if Q is positive, even if it's small, S prime will successfully invade a population of alt. Sorry? Assuming mistakes. Assuming a positive probability of mistake.
Assuming there's not an S double prime that exploits S prime, because S prime is very exploitable, right?
We're not saying that S prime is evolutionarily stable. All we're saying is that alt is not evolutionarily stable. That alt will be successfully invaded by some strategy, S prime. Now, S prime, in fact, is not evolutionarily stable either, because S prime, as you say, is exploitable. But that doesn't matter in the demonstration that alt won't survive.
Did you say in a previous slide that alt is not invadable?
Yeah.
When there are no mistakes. Alt is not invadable when there are no mistakes, but alt is invadable when there are mistakes. So this is the this is
No mistakes, that tit for tat is not. So tit for tat will be evolution stable even with mistakes. Is that correct? or not?
no. Tit for tat is not evolutionarily stable because with mistakes, actually, it's going to get it's going to do very badly. If tit for tat plays itself, there's going to be a long sequence of recriminations. Now, I'm going to get to what is evolutionarily stable a bit later on, but tit for tat is not evolutionarily stable. But in some sense, this is the central idea of the talk. This slide is the central idea. So let me pause and make sure that you're all with me. And I should say that what I'm talking about in this lecture is work that I've done with Drew. Some of it's published. Some of it is in an AER piece from 1990. And some of it, for reasons that cannot be blamed on Drew, but can certainly be blamed on me, is not published, but it exists in working paper form. Okay, so I will assume from your silence that you're with me to this point. So what I'd like to do from this example is to generalize the logic and talk about two-player symmetric repeated games. Now, the two-player part actually is not so important. Basically, everything I have to say could be done for n-player games, but the symmetric part is important, and you will see why it's important later on. And there are two results that I want to talk about. I'll spend a reasonable amount of time establishing one of them carefully, or at least moderately carefully. The other I will do a lot of hand-waving on. But I think you'll understand both of them pretty well by the end of the talk. So the first is the idea that we saw here in the alt example. If a strategy is evolutionarily stable, and if there's not too much discounting, and for my purposes, it'll be easier to work with discount rates rather than discount factors. So the discount factor delta is 1 over 1 plus r, the discount rate. So I'm assuming that everyone has seen the distinction before. So I'm going to work with discount rates, which are small. If a strategy is evolutionarily stable and the discount rate is small and the mistake probability, p, is small but positive, then there's a sense in which S, the evolutionarily stable strategy, must be almost efficient. And I'll be more precise about this very soon.
Mistake probability means every period there is probability P of mistake IID over periods?
Yes.
Is that the model you should
That's the model. Again, I'll make that more precise in a minute. So I'm going to state these results more carefully later. This is the very informal statement. There's a converse result, which says that if we start with payoffs that are efficient, and I'm put efficient in quotation marks because the notion of efficiency that we will be using is somewhat different from the standard notation and concepts, and I'll make that clear. But if we have efficiency in this sense to be defined, then there will exist evolutionarily stable strategies which attain those payoffs, provided that the discount rate is small enough. And furthermore, and this is a point that doesn't come up in the first result, the mistake probability is small relative to R. And you will see why both P and R are small, but it's important that P be small relative to R for this second result to hold. So those are what I'm aiming for.
So they cannot hold in an undiscounted kind of limit value, because then P has to be 0, and then you lose the fraction of that.
Yeah, well, all right. So I should say that Drew and I originally looked at an undiscounted world where with lexicographic considerations. So P was infinitesimal, and the idea was that in order for a strategy to invade, it had to do well, it had to do better, it had to do just as well as the dominant population when there were no mistakes. It had to do strictly better when there were mistakes. When there was one mistake, if there was a tie there, you would look at what happens if there were two mistakes, and so on. So lexicographic consent. You can do it with zero discounting if you look at the number of mistakes in lexicographic order.
If P can be high, if P is high and R is small, it's better.
If
If R is small and P is high,
It-
it's better that P is high for the mutant.
it might be better for the mutants, but it's not so good for efficiency. Yeah, you'll see why. Okay, so that's where we're headed, and now let me show you the model. Finite symmetric two-player game. So symmetric just means that players have the same action spaces, and if you permute their actions, you also permute their payoffs. And I'm going to normalize the payoffs so that the minimax payoffs are 0. So I talked about this in the first lecture, but we can look at the set of feasible payoffs feasible in the repeated game, where we look at the convex hull of the there should be a greater than 0 here. We look at the convex hull of the payoffs that are individually rational, payoffs which give payoff.
He wants intersections up to plus.
Yeah. Right.
He means intersections up to plus, also individual
Right.
rationality. Individual rationality.
Yeah. Feasible and V star is feasible and individually rational. Yeah. So I left out the individual rationality. All right. So now we come to a concept which is not so familiar. What I'll call strong efficiency. A feasible pair of payoffs, V1 star, V2 star, is strongly efficient if it maximizes the sum of the two players' payoffs.
Diagonal. Which says also that implies that it's on the diagonal. So also V1 star must be equal to V2 star.
No, it does.
In the convex sum of the symmetric set, the set is symmetric.
Here are two examples of games that you're familiar with. This is the prisoner's dilemma. The prisoner's dilemma has a unique, strongly efficient point, 2-2. But this is the battle of the sexes. The battle of the sexes has a this is has two vertices on the Pareto frontier. Any convex combination of 1-2 and 2-1 is going to be strongly efficient in the battle of the sexes, right? So, and this distinction actually turns out to be important. There's a big difference between the prisoner's dilemma, which has a unique, strongly efficient point, and the battle of the sexes, which has a continuum of strongly efficient points. And you'll see why that distinction is important pretty soon. But for now, let me say why strong efficiency is even relevant. You might wonder, how could it be relevant? How could adding up payoffs across players be a relevant consideration? I mean, that looks like we're making interpersonal comparisons or something like that, but that's where the symmetry of the game comes in. Imagine that we have this population of players, and we're drawing pairs of players at random to play the repeated prisoner's dilemma or the repeated battle of the sexes. Whether you're assigned the row player's position or the column player's position is equally likely. In fact, in some sense, there's no distinction between a row player and a column player. It's a symmetric game. And so really what's relevant is what your average payoff is after there have been many random draws, after you've had a chance to play the repeated game many times through this random drawing process. This is, if we divided by 2, this would be your average payoff from playing the game. So strong efficiency comes in because of the fact that you have an equal chance of being the row or column player.
And that the players are not identified. It's not like
Yeah.
you are player 1 and you are player 2.
That's right. There's
Because
only one
if
population.
you give them labels, then they
That's
can
right.
use that to get an unsymmetric equilibrium.
Exactly.
They don't get labels.
They don't get
Or any
labels.
outside signals.
That's right. So that's strong efficiency. And as usual, we will repeat these games infinitely many times, but we can interpret the discount factor as the probability of continuation, so it doesn't literally have to be infinitely repeated. Just a piece of notation, at any time t, we'll be interested in the history of the game up to time t, which is just the pairs of actions that have been played in the previous t-1 periods. And I will use the notation pi of h, where h is a history, to denote the mirror image of h, where we've just reversed the 2 components of each pair. So pi of h is h from the other player's point of view. And a repeated game strategy is just a mapping from the set of histories to randomizations over actions. Actually, for my purposes today, let's just look at degenerate randomization. So you either play an action with probability 1, or you play it with 0 probability. And it'll turn out to be convenient, although this is not actually essential, to assume that strategies are finitely complex, which means that they could actually be played by a computer with a finite memory. A finite automaton, right. Not a very strong assumption, but it's not actually, it makes some of the arguments.
It's not a Turing machine.
It's not a Turing machine. A Turing machine has an infinite tape, that's right. It's a finite automaton. As actual computers are, or actual people are. So in each period, there's a probability that a player does not execute the strategy S that it's supposed to execute. It makes a mistake, and we'll suppose that, again, this is not essential, but it'll be convenient to assume that all mistakes are equally likely.
You're admitting mixed strategy here.
No,
What's the delta mean?
well, yes, so I was admitting them, and then I immediately took away the delta by saying that for my purposes today, I'm only going to look at pure strategies. Okay. But I have the delta there because it turns out that we can accommodate mixed strategies. I'm just not going to talk about them. Sorry?
Randomize it or whether you're using them or not.
Right. And Sergio already anticipated this point that mistakes will be independent across periods and across players and across periods. I don't actually have the periods there, but I want that too. So that's the model, and using that model, we can derive this very ugly expression which you're not going to want to digest, but formally this is just the payoff to player 1 if he uses strategy S1 and the other player uses strategy S2, given that there's a mistake probability P and a discount rate R. This is the discounted average payoff. Don't worry about digesting it or even copying it down because the slides will be available. And you can look at the same thing assuming that history H already occurred. So this would be discounted average payoffs contingent on history H already having occurred. Notice that because all mistakes are, all actions are have positive probability, all histories have positive probability. So all histories are possible. Okay, so now we come to evolutionary stability. I've already talked about evolutionary stability informally, and it's just the idea that if we have a large population, if most of the population is playing S, no mutants can successfully invade, which means no mutants can get an expected payoff which is higher against the mixed population than the prevailing strategy can get against that population. And a more careful way of saying that is that a strategy is evolutionarily stable with respect to parameters Q, R, and P. I've already talked about R and P. Q bar is an upper bound on how big the mutant population can be as a proportion of the overall population. So if the mutant population were big enough, then nothing could be evolutionarily stable. So there have to be some limits on how big Q bar is. And for Q less than Q bar, we want this inequality to hold, which just says that strategy S against a population consisting of S and S prime does as well against that population as any mutant strategy S prime. So this has to hold for all S prime. I have a strict inequality here. We could do just as well with a weak inequality, but it's a since we have mistakes, and since all histories are possible, it turns out we can work with strict inequality as well as with the weak inequality. That is, the chance of having an exact tie is zero in a repeated game where all histories have positive probability. Now the way I've expressed evolutionary stability is as a static concept. That is, I haven't explicitly shown you the dynamical process for which S is a steady state or a persistent strategy. I think I will refrain from spending time on the dynamical process, except to say that there are dynamical processes which give rise to exactly the concept that I showed you of evolutionary stability. And if you want to see one of them, it's on the slides, but I'm going to skip over those slides now. And I'm going to skip over the formal result connecting the static definition to the dynamical process. But again, you can read that on your own. Instead, I want to get to the results I already told you about. And to do that, let me, yes? I'm sorry.
I'm wondering if this S prime
Yes.
is coming from the whole possible set of strategy, or you're giving this set is kind of restricted. The mutants can take any possible.
Yes. Let me go back to the definition of evolutionary stability. This inequality has to hold for all S prime, for all repeated game strategies, well, finitely complex, all finitely complex repeated game strategies.
Yes, but this S prime is for the small population, right? So my question is, you're restricting the set of possible, like from S prime can come from, or could be any possible strategy.
Any possible strategy, yeah. Any possible strategy.
To that, would it make a big difference to assume that this strategy is evolutionary stable itself? So the question is, could we define another notion which is a strategy is evolutionary stable?
Okay, so you're saying should we narrow down S prime by requiring that you have some sort of recursive definition? We could do that, and there might be circumstances where we would want to, but of course that would weaken the concept of evolutionary stability. You would get more equilibrium, potentially more equilibria that way. That's right. We've given some thought to that, and qualitatively, it actually doesn't change things very much. But for today, we're not going to require that S prime be evolutionarily stable in the same way that when we talked about alts getting invaded by S prime, we didn't require that S prime be evolutionarily stable itself. Yes?
You assume that the chaos are non-generic in the sense that you're never indifferent between two actions or something like that?
Well, I'm assuming that players are using pure strategy. This isn't important, but for the presentation, players are using pure strategies. Because let me just stop there.
Then I have a related question. If there are two actions that are identical in payoff,
Yes.
can there be an evolutionary stable strategy? Is this strict inequality?
Okay, so you're right that this requires some restriction on the payoffs of the stage game, but for some generosity restriction. That's right. If, for example, all the payoffs were zeros, then everything would be then nothing would be evolutionarily stable, because any other strategy would also always give you zero. That's right. Okay. So let me get to the first result that I'm going to talk about. And to do that, it'll be helpful to look at the minimum payoff, the minimum feasible payoff that is consistent with strong efficiency. Maybe it would be helpful to look at the two games that I've been talking about. In the prisoner's dilemma, there's only one strongly efficient pair of payoffs, 2-2. And so V lower bar is just 2. But in the... that's right. Here's the picture of the Battle of the Sexes. In the Battle of the Sexes, the minimum payoff that is consistent with strong efficiency is 1, because if the other player has a payoff of 2, the payoff pair 1-2 is strongly efficient. So here is the first result, which is the result saying that if you're evolutionarily stable, you must be efficient in a certain sense. This was the efficient in quotation marks. Basically, you have to have an average payoff which is not much lower than V lower bar. You have to have a payoff which gets you at least V lower bar minus epsilon. And for
it says they only get 1-1. They could only get 1-1, which is very far from being efficient in some sense.
Right. So in the Battle of the Sexes, it turns out you can any payoffs between 1-1 and 3/2 are going to work as far as this theorem goes. But for the prisoner's dilemma, by contrast, you can guarantee efficiency in the usual sense. Payoffs will have to be very close to 2-2 in order to be evolutionarily stable. And let me show you how this is proved, and then I will come back to the contrast between the prisoner's dilemma and the Battle of the Sexes, why they look so different from the point of view of this result. But before I get into the proof, are there any questions about the statement of this theorem? Is it clear what is being asserted? Okay, so here's the idea. Suppose we had an evolutionarily stable strategy S, which actually delivered a payoff less than the lower bar after some history, H. And what we'll do, and this is very similar to what we did when we showed that alt was not evolutionarily stable, we'll construct a mutant S prime that can successfully invade. And here's how S prime works. First of all, we want to look for the history H star which minimizes player one's payoff in the continuation game, starting from H. And here's one place where we're using finite complexity. Because strategies are, because S is finitely complex, there are in effect only finitely many histories that we have to, there are only finitely many equivalence classes of histories that we have to consider. And so this minimum exists. And in particular, this bad history leading to bad continuation payoffs for alt would be any history where there's been a failure to alternate at some point. So what S prime will do is to behave exactly like the prevailing strategy, S, for histories which are not either continuations of H star or its mirror image. So for most histories, S prime does exactly the same thing as S. But because of mistakes, all histories can occur. And eventually, H star will occur. And so that's where the action is. After H star, S prime will, in effect, signal its willingness to cooperate by doing something different from what S does for one period. Now, I'm ruling out mixed strategy. So in particular, S is not randomizing. If S were randomizing, it might take more than one period for S prime to distinguish itself from S. It might have to do something, use different probabilities for a number of periods so that statistically it could be distinguished from S. And that's the main complication in working with mixed strategies. But today, no mixed strategies. It just does something different for one period. Let's suppose that I'm going to suppose for the purpose of this argument that H star is not equal to its mirror image. So things look different for player one by the time that H star has occurred than for player two.
So you pick just one H star. There may be more than one.
There may be more than
For
one.
example, pi H star will be another one. So you have no fixed just one out of those, and the minimum is attained.
Yeah, pi of H star, the minimum might not be attained. Right? It depends on.
It's SS, no? It's symmetric.
No, but the histories aren't symmetric. The histories aren't symmetric. There's nothing to say that H star has both. Remember that mistakes are possible.
Payoff of player one now.
Right.
Player one.
Player one.
Okay.
Right.
But anyway, there is
Yes.
just one history now that we are fixing.
That's right.
Even if the minimum is attained in many ones, we are
Ex-
fixing one.
That's
example.
right.
Okay.
That's all that we.
All of the-
That's all we need
all
to
the
do.
equivalent ones.
And H star is different. I'm just going to assume that H star is different from pi of H star. So S prime is going to do something different for one period if the other player in the following period responds by not doing what S would do in the following period, but doing something else. Then S prime, from that point on, is going to do something which is consistent with strong efficiency. So for the prisoner's dilemma, that means it's going to cooperate in every subsequent period. Let's think of the prisoner's dilemma for now. I'll talk about the battle of the sexes later. That's slightly more complicated. Prisoner's dilemma, S prime will cooperate in all subsequent periods, provided that the other player has responded positively to its olive branch. And now I want to compare S prime with S, and I'm going to show you that S prime does better than S. Well, because H star is by definition the worst history, or the history for which subsequent payoffs are worst, S prime, by signaling for this one period, can't lose very much. It might do very badly that one period, but the worst that can happen starting in the next period is that S prime gets this worst continuation payoff starting in that period. And if there's not very much discounting, that loss is not very big. Furthermore, if the probability of mistake is very small, the probability that the other player really is S prime and not S is with high probability detectable after one period. S will do its thing. S prime will do something else. Of course, there's a probability that either of them might have made a mistake, but P is assumed to be small. So that's not very likely either. Now, S prime, by construction, does essentially the same against S as S does against itself. It does the same as S against after any history except H star. After H star, it doesn't do quite the same thing as S, but if it's playing S, it only differs from S for that one period. So, and then of course S prime does very well against another S prime. It gets to strong efficiency. So we can make a table. Actually, we can make two tables is this visible? Okay. Comparing S to S prime. And the relevant histories to start from are H star and pi of H star, which are equally likely from the standpoint of player 1. S against itself gets this worst continuation payoff. So let me call that M for minimum. And S prime against S also gets M. And S against S prime also gets M. S prime against S prime gets some other payoff X, and over here I'll put 2 minus X because remember we're looking at the prisoner's dilemma, and the strongly efficient payoff is 2. So if over here we get X, we have to have 2 minus X over here to add up to 2. Now, I've said that that we're looking at payoffs which are less than the lowest payoff that is consistent with strong efficiency. For the prisoner's dilemma, 2 is the strongly efficient payoff. This payoff, whatever it is, let's call it M prime, has to be such that M plus M prime is strictly less than 2. That is, the two players together cannot be getting payoffs that equal 2, because that would be strongly efficient. And so we see that on average, S prime does strictly better than S, since S is constrained to be getting payoffs less than the strongly efficient payoff after H star. This is just a generalization of the argument we used to argue that alt was invadable. And so, indeed, S is not evolutionarily stable. Now, let me show you how that argument plays out in the Battle of the Sexes. This is actually not the Battle of the Sexes. It's the Battle of the Sexes amended to add on a couple of extra actions. The strongly efficient payoffs for the battle of the sexes are here and here. The average payoff, the average payoffs will be 5 halves for either player. But I want to show you that we can construct an evolutionarily stable strategy in which players get less than 5 halves, in particular payoffs of 2. And the way this is done is to look at a strategy which plays D, and so if the other player is also following this strategy, will result in payoffs 2-2, as long as players have always played D in the past. And now, if somebody deviates, if say player 1 deviates from D, go here forever. That's strongly efficient. If player 2 deviates, go here forever. That strategy S cannot be invaded. And the reason it can't be invaded is because the punishments themselves, going here or here, are themselves strongly efficient. Notice that the way that we got a successful invasion of a mutant was to exploit the inefficiency of the prevailing strategy after the strategy got off the equilibrium path. So alt was very inefficient off the equilibrium path, and in the more general argument, S was failed to be strongly efficient off the equilibrium path. But in the battle of the sexes, we can make sure, because we have available this large set of strongly efficient payoffs, that we can tailor make the punishment for the player who deviated. We can punish that player in a strongly efficient way.
So 2-2 is not strongly efficient.
That's right.
So
But the problem is, if you're say
it is evolutionarily stable. Yeah.
this strategy is evolutionarily stable because say you wanted to invade this population.
Okay.
Well, on the equilibrium path, you would have to do the same as S. Otherwise, you would be killed, right?
So what you're not saying that all the evolutionarily stable strategies are in this setup where you have computers and mistakes and so on and
Yeah.
so forth. Yeah. You're not saying that all the ES outcomes are strongly stable, strongly efficient.
I'm not saying that. I'm saying that they have to be consistent with the lowest possible one-player payoff.
Okay.
So in this game, they have to be at least 1-1. And here's an example of where they're 2-2. This is not strongly efficient, but it is evolutionarily stable.
The alternating gets 2.5, 2.5. The strategy that alternates gets 2.5, 2.5 with A, B, and B, A.
Yeah. So there are strongly efficient evolutionarily stable strategies, but there are also evolutionarily stable strategies which are not strongly efficient. And for for this game, any payoffs, what did I do with the chalk? Yeah. Any VV such that V is between 1 and 3/2 can be sustained in an evolutionarily stable way. And in particular, you can get 3/2 by, 5/2. 5/2. You can get 5/2 by going back and forth. Right. Okay. So I hope this makes clear the distinction between the battle of the sexes and the prisoner's dilemma. The crux of the matter is that in the battle of the sexes, you can punish any player while still maintaining strong efficiency. You cannot do that in the prisoner's dilemma. Nevertheless, in the prisoner's dilemma, we can get evolutionary stability, and in fact, evolutionary stability forces us to payoffs very close to 2-2. How do we do that? The way that we constructed these mutants was by exploiting inefficiencies. To avoid having such mutants, we have to look at strategies which are as close to as close to strong efficiency as possible. So we need punishments which are over as quickly as possible. And for the particular payoffs that I've been looking at in the prisoner's dilemma, the 2-2-0-0, 3-1 payoffs, here is a strategy which is evolutionarily stable for R and P close to 0. S plays C if last period we had CC or DD, otherwise S equals D. This is a strategy which is sometimes called perfect tit for tat. It's called perfect tit for tat because it is a subgame perfect equilibrium against itself. It's sometimes called win, stay, lose, shift. It's come up several times in the summer school. And here it is again in a different setting. This is an evolutionary setting. Notice that this is a very good way of punishing someone. If players are going along cooperating and someone deviates, say by accident, as will occur occasionally, in the period of the deviation, we will have one player. This is with high probability, we'll have one player playing D, the other player playing C. According to this strategy, the next period, both players will play D. But the following period, they'll go back to cooperating again. So we have one period punishments, which are sufficient given the parameters that I've laid out. One period punishments, very forgiving. And that's exactly what we need to avoid these mutants which exploit inefficiencies. Well, I'm running out of time, so let me just state the converse theorem, which says that for evolutionary stability, if we take payoffs that are consistent with strong efficiency, that is, both players are getting at least v lower bar, then we can construct an evolutionary stable strategy which attains those payoffs. I've given you an example for the prisoner's dilemma, but this can be done more generally. Yes, when the game starts out, where the two players are symmetric, so from the beginning of the game, the payoffs that players are expecting must be the same. Now, notice in the statement of this theorem, I mentioned this at the beginning, P in general has to be small relative to R. So let me explain why that's the case. I have that someplace here. Yeah. Let's look at this modified, this perfect tit for tat that we've looked at. And let's suppose that perfect tit for tat plays against itself. Now it's going to start out cooperating, but there's always a chance that a mistake will be made. Now every time there's a mistake made, if say player 1 deviates, there will be a loss in overall expected payoff. 2 is better than 3 minus 1. In the period where the mistake is made, the loss is this expression here. This is what a player would get if there were no mistake. This is his expected payoff when a mistake is made. Either he will make the mistake or the other guy will make a mistake. If he makes the mistake, he gets 3. If the other guy makes the mistake, he gets minus 1. So there's a loss of 1 in that period. And then there's also a loss the following period where both players are playing DD. There's a loss of 2 in the second period. So the overall expected loss, given the probability of mistake and the discount rate, it is this expression here. This is the expected average, discounted average loss from mistakes. Now let's suppose that we introduced a mutant strategy which starts out cooperating. But if we ever get off the cooperation path, it signals in the same way that our constructed mutants earlier today signal. But once it gets a response from the other, a favorable response from the other player, it never punishes at all. So it doesn't have this second period punishment. Well, the loss that this strategy incurs against itself is lower. And Now, these are only approximations. But if R is small relative to P, then that shows that the mutant will do better than S. That,
Only for that any relation. It's only for that argument any relation between P and R. That is a higher loss than that. That's a problem.
yep. No, these are only approximations. The approximation, yeah, it's a first order approximation. The second order considerations will take over if R and P are of approximately the same magnitude. But for R much smaller than P, then this will be a first order consideration, and you will be better off not punishing. And intuitively that makes sense if relatively speaking, deviations are occurring because of mistakes. It's not a good idea to punish.
P having P small means there is enough time to get the rewards of the strategy against itself.
Right.
If P is too large, then mistakes and discount are the same. So there is not enough periods where you get rewards to accumulate.
Exactly.
And the small P says that until the next mistake, there is such a long time that you accumulate something that makes it better.
But despite the fact that I've been talking about infinitely repeated games, my time is up, and I will stop here. Thank you.